people 5 minutes to drift in, and if people drift in later, it's not too much of a problem. Hey, what do you know? Okay, welcome everyone to the Power and Electricity training session. This has been put together by Tom Strong and myself over many long nights and tables and drama. This is version 2 of the slideshow. I have made corrections based on the alumni and other people complaining about things that I said wrong. So thank you everyone who helped to that process as well.
Is this correction since the one that I used?
Yes. Including some of the things from Alex took some notes of your show presentation, and I have implemented them. Okay, so today we'll be talking about a few different things. Fundamentals of what is electricity, a bit about power transmission, and then a good chunk about what hardware AB Tech and kind of SNS have to deal with, and what they all mean and how they work with each other. So first, fundamentals of electricity. Our first fundamental concept is voltage. It's measured in volts, and it's called electric potential, but you can think about it as the motivating force that moves the electricity through the wire or circuit or whatever you're doing. If you're thinking of terms of water and pipes, which is a really good analogy, it's the equivalent essentially of water pressure. Second fundamental constant or variable is current. Use the letter I, measured in amps or amperes if you want to get long and fancy. And this is the rate of flow of the charge carriers, usually the electrons. If you're getting fancy, it's also holes in 220. And this is the flow rate of the water through your pipe or wire. That was the wrong button. Power is the amount of energy spent per time, measured in watts. And you can easily calculate power by multiplying your voltage and your current through the nice clever equation of P equals IV. And it so is convenient that 1 watt is equal to 1 volt times 1 amp. Is everyone good with these so far? Not too complicated. Our next fundamental is resistance, which is, as the name implies, how much the flow of electricity is stopped or held back or resisted. Measured in ohms, and it is something you get by running your electricity through some kind of device, wire or light bulb or whatever the case may be. Except for superconductors, they tend to not contribute that much. And usually resistance is burned off as heat. So the energy, due to conservation of energy in the universe, you don't lose the energy, it just turns into heat and goes elsewhere. Okay, load types. So different things behave differently when you try and run electricity through them. You have resistive loads, which are your lamps, strobes, computers, MLs, and LEDs. Some of these are actually on switch mode power supplies, which act a little weird, but they essentially make the math work out so they can be viewed as a resistive load. And these you can easily use the equation V equals IR for doing your math. The other kind of load are inductive loads. These are really dimmers and anacondas. And somewhat lamps, but not as much. And inductive loads are special because when you have alternating current, which we'll talk about in a couple minutes, they do weird things to the current timing and make the math more difficult.
Point out the MLs are not purely resistive loads, they're switch mode power supplies. So they act resistive, they have a power factor of 1, but they do not follow V equals IR.
Okay, cool. Okay, thank you. Yeah, if I miss something or say something wrong, please correct me if you do know more than I do about that subject. So here's an example to prove that these variables actually make sense. So we have 4 source 4s. Each of them has a 575 watt lamp in them. We want to plug them all into one circuit. How much current will we draw to make sure it is safe? So we have our basic equation, P equals IV. 4 times 575 watts equals current times voltage. The wall voltage is 120 volts, and you can get a total of approximately 19.2 amps for the 4 source 4s. Simple math, hopefully. Okay, is everyone happy with our basics of electricity? Cool. Next, power transmission. Getting power from one place to another, you don't always, want it to be at the same voltage, so you have these handy devices called transformers. They change the voltage of the circuit from one level to another with some degree of efficiency. And they either step it up or step it down depending on where they are in the process. So if you're at a power plant, you're probably going to see step-up transformers to make the voltage higher. As you come down the power lines from the high voltage lines down towards your house, you're going to get step-down transformers successively bringing the voltage lower and lower. And they also really only function on AC current or AC circuits, which we'll get to in a minute. Okay. So I keep saying AC. What does it mean? Well, it's the opposite of DC. DC is direct current. Essentially, it means that the voltage or the current is always flowing in one direction, pretty much the same rate all the time. I mean, it could vary, but it's essentially the same. So when you have small electric circuits, say an ECE lab, those are usually DC circuits. And if you think of water in a pipe, it's just the water is always going in one direction. On the other hand, you have AC current. With AC current, you have the voltage oscillating back and forth in a cycle, which is driven by whatever's creating the voltage supply. And the current will, to some degree, follow along with that voltage, going back and forth. So it'll go above zero and below zero, or it may be offset by some DC current, some DC voltage to just oscillate among positive numbers. Voltage is all relative between 2 points, so there's no absolute true zero. Also a note is when you're measuring AC voltage, you don't usually measure the peak to peak of the wave. You measure the average of the wave using a formula called root mean square, which essentially is you add up everything, take the mean of it, and then add up everything square, all the values squared over time, take the average of that, and then square root it, right? Root mean squared. So that's RMS, it's how you measure voltage. And 120 is actually the root mean square of the signal. So single phase AC, you have one line which is your hot and one line which is your ground or your neutral. Your neutral is designated 0 volts, and the voltage on your hot will oscillate up to a max of 170 volts, down to negative 170, and back and forth in a beautiful sine wave. However, the peak isn't really that important. It's the root mean square of the signal because the shape will vary, but you want the RMS to be the same, and the RMS will be approximately 120 volts, hopefully. If not, you might need to get your wiring checked out. And that's single phase AC. Does that make sense to everyone? Because we're adding more. Okay, 120 and 208 volt three-phase AC. So what this does, the way this is you have 3 hots and 1 neutral. And each of the hots is oscillating 170 volts peak to peak, 120 volts RMS relative to the neutral. However, each of them is offset in time by 120 degrees. 360 degrees makes a whole circle. So if you went 360, you'd be back to the first one. So this one's 120 off, this is 240 off. And the effect of this is, for each of these 3 ACs, you get each of these lines, you still get 120 volts RMS if you measure them to the neutral. However, if you measure them relative to each other, you get 208 volts, which is convenient because if you remember the power equation and resistance, for some things, when you run them at a higher voltage, you use lower current. This is why power lines, which run across the country, are all very high voltages. They're all in the hundreds of kilovolts range, because that way they can operate at very low currents and thus use less energy as heat. So you can see this fun animation of here's your power station generating the AC, and you can see the 3 lines going in sequence and then into and out of the load. And so an additional fun thing about this is if you have equal loads on all 3 phases, then the approximate current going through the neutral will be 0. Because what will happen is when the current's flowing from black to neutral, it'll then flow backwards a little bit into each of red and blue, which reduces the amount of current going through your neutral and can be convenient at times. Does that make sense? Okay. So I thought I moved that around. So in some places on campus, tech needs 3-phase AC because a lot of our gear is based on having all 3 phases present and then tapping off each of them individually. You can tap each of the 3 phases individually, or you can tap them in pairs and get the 208 volts. So sometimes, such as at Carnival or on the Baker lawn, we need 3 phases, but only 2 of them are provided to us. So we do this fake 3-phase system where we feed phase 3 from phase 2. On some of our power distribution units, Sound PD and the new MLPDs, they can output feeder to another device, but what we do is we output the second phase and feed it into the third phase. This is called trick legging, and you should really only do it if you know what you are doing. This does not count as telling you that you know what you are doing. That's my disclaimer. And what this gives you is you get 2 phases, or you get essentially 3 phases where you can measure hot to neutral and get 120 volts. You have your Y, your Z, and your X, but you get 2 phases of 208 volt. However, you remember on 3-phase, you have 3 208 volts. Here you only have 2 because 2 of your phases are exactly the same thing, so the voltage between them is 0. This is really only beneficial when you need a bunch of 120 volt lines and you're just using the gear that provides 3 hot lines and distributes between them. You don't really want to use this as much when you need the 208 volts on all 3 phases, because that puts a lot more work on the ME to figure out which one is which and making sure that the balance is better. Because there are 2 hots, you lose the capability of having all 3 phases balanced and having almost 0 load on the neutral line. Because 2 of them are the same, you could actually double the load on your neutral at times, which on cables such as L2130 is not designed to handle that, and you could do some damage to it. Does this make sense? This is getting a little fancier. Yes?
When you say double the load, what's that relative to?
Well, if you're pulling 30 amps on the Y phase and 30 amps on the Z phase, you're going to be putting a little bit's going to go back to the X phase because that's going to be a low flow out, but a lot of it's going to be going into the neutral. And if the cable's built so only 1 phase at a time is maxing out its load because the current follows the voltage, then, so at this point, there's 0 here, but there's 2 of them here. And the cable's the neutral's only designed to have 1 of them at a time. So that was 208 volt power. There's also something 240 volt power, and according to Floyd, that's what we actually have at Carnival. It's not 2-phase -1. I'm not sure, but
Depends on where you're talking.
so different places have different things. But 208 volt power is you have 3-phase power, that's 120 208 volt, and you take one of the phases away, and that only leaves you with 2 phases. And that leaves you with this shape here of you have 1, and then 120 degrees later you have a second, and then 120 degrees later you have nothing, and then 120 degrees later you have the first one again. There's also a 240 volt system of multi-phase AC called split phase. And what this is it's actually 1 phase, but with 2 opposite poles that oscillates back and forth to positive and negative 170, and they're at the same time. The neutral splits it down the middle, and this gives you a 240 volt RMS if you go between the 2 of them, and 120 volt RMS to go to the neutral. There is no 3rd phase. There's not even really a 2nd phase there. It's 1 phase that just mirrors itself. So we just talked about 3 different ways of conveying multiple phases. This is kind of what they look like. I'm also going to do a diagram. Can everyone see the chalkboard over here? Okay. So that's what they look like in a linear time-dependent way. You can also look at them on a weird graph of your voltages. So if you have your neutral in the middle, which I will label N, then your normal 208 volt 3-phase looks kind of like a triangle, where this is your positive voltage, and this is your negative voltage, and then this is negative imaginary and positive imaginary. Yes, I switched my axes. Tom, are they imaginary voltages, or?
It's not, voltage is distance from center on this type of graph,
Okay,
and phase going around.
okay, so there's no positive.
Like that.
What?
It's like a polar graph.
Yeah. But,
There's no plus or minus V. It's 0 at the center and R
okay.
is V.
But this point here is X, Y, and Z. And if you measure any of them to neutral, you get 120, and if you measure between them, you get 208. And what happens is, over time, these rotate, and if you think of this, that currently the x is at 120, and as it rotates around the circle, your circle rotates, the other phases will come up and turn to positive and go negative. Right, Tom?
Yeah.
That's why I labeled this positive V, negative V, because if you...
Phase space doesn't really map to a Cartesian plane.
Okay. Does this make sense? So that's 208, 120. 240 has the triangle. No. There's actually a third weird variant, which has the neutral here, 120, 120, and 180 up there. So this is called, yeah, this one's evil. You never want to deal with this one. I had to deal with it over the summer because you have two phases that are normal 120, and it gives you about 230 between each of them. You have two phases. The system I had 230.
Not at 120 plus 120.
Maybe my neutral was like sitting over here or something.
The way you can spot that one, usually one of your cables, your wild leg, the 180, will be orange. If you see an orange color-coded cable, just walk away. The other way is if you look at a breaker panel with single pole breakers, it'll be 2 rows of breakers and a gap, 2 rows of breakers and a gap, 2 rows of breakers and a gap. The gaps in the wild leg.
And the reason that is because your neutral's here, you get 120, 120 to the neutral, but this guy's 180 to the neutral, and you can't plug normal stuff that wants 120 into a 180 line.
That's in order to provide 240 to the.
It gives you 240 between each of the poles.
Require 240.
Right. And it gives you 2 phases of 120 and 1 phase of don't touch that by itself. And then the split phase. Split phase is 120, 120, 240 over the whole thing. I'll leave those up so you can look at them. Does everyone understand the difference between these 3 diagrams? So in the future, when you talk about 3-phase power, you understand what 3-phase power is, or 2-phase, or split phase, or why is there a cable coming out of the blue and going into the red at Carnival? And you stand there confused and like, oh, Floyd explained it, it makes sense. Not really. This is why. And I'll get into later why we actually want that 3rd phase to be there, even though we lose one of the 208 volts. So now we're going to switch into hardware. And first we're going to talk about cables. And one of the most important aspects of our cable is the wire gauge. The gauge is a measure of how thick the cable is. And the bigger the number, unintuitively, is the smaller it gets. Although it's convenient because the number actually means that many cables will take up the same space. So apparently 34 gauge cables takes up the same space as 12 gauge cables.
If there was no insulation.
Yeah, just the copper. So I guess that's where that number comes from. And as your cable gets thicker, the thickness increases, the weight increases, but also the ampacity of the cable increases. Because if you think about a pipe of water, the bigger your pipe is, the more water you can shove down it at a time. Same theory applies to electricity. Because wires don't have a 0 resistance. They have a very low resistance, but it's non-zero. And therefore, a thicker wire, in fact, will have a lower resistance and allow more current to pass through it without burning off into energy. So greater thickness, low resistance. Because it's lower resistance, it's going to convert less energy into heat. Because there's less resistance, you're also going to get less voltage drop, which I'll talk about in a minute. And greater thickness means it's going to be heavier, so it sucks if you're rigging and your ME wants to put a bunch of heavy cables on. So another look at wire gauge. Each cable or each gauge is rated by the NEC for a certain amount of rated current. However, these are baseline values and they change due to a number of factors, due to how long your cable is, what temperature it is, what kind of insulation you have on it, what temperature the cable insulation's rated for, whether it's in the sun, and all these different things. So for the cables that you deal with a lot are 14, 12, 8, 1/0, 2/0, and 4/0, and those are approximate current capacity baseline values that can change. Does this make sense so far? Does this make sense? I pulled this off the wiki. It might not be up to date or accurate, but you have your cables, the diameter in, what units would you say those are in?
Inches.
Okay. Cross-sectional area, probably in mils.
1,000 circular, in circular mils.
Okay. But a mil is a millionth of an inch,
1,000.
or a thousandth of an inch.
A circular mill is.
Like squared, but or
The
circular.
area of a circle, 1 mil across.
When you're in a shop, you'll hear mils a lot because it's like the imperial equivalent to like millimeters.
So why would we just use millimeters?
Because this is America.
It's America. We use the metric system.
Okay, that doesn't answer the question why they had to make a circular unit.
Well, because square mils wouldn't make sense.
It's
These
the
are cables. They're circular.
area of the cross-sectional area of a wire that's a 1 mil diameter.
Okay.
And since the cross-sectional area is what really matters, they just start with a very small wire. And when you get up past your 4/0, like 250 MCM is 250,000 circular mils, which is why the area column suddenly gets to very round numbers there. When you look at very large wires, you just measure it in the cross-sectional area.
So the important thing here is the cmuENC. I'm not sure what ENC stands for. I'm guessing. Okay, so it's got insulation around it, and the current capacities for them.
Opposed to hung in free air.
Okay. You also get air. You also have aluminum. You have its resistance per foot, which is, as you can see, non-zero. Yes.
So the cmuENC is like amperage?
Yes.
Okay.
These are your approximate amperage values. And you could tell that even though a wire is of a certain gauge, the values can be different depending on where it's running and what material it's made out of. You also have convenient numbers like the weight of the cable. So
6 pounds per foot?
Yeah, it's a cable that's 1.6 inches in diameter. Or conductor. Either way.
6 pounds per foot. Who cares?
you run it on the ground and never touch it again. But the point is, gauge isn't a be-all, end-all. It varies. There's also a temperature scaling factor. These are all for, I believe, 30 degrees Fahrenheit or Celsius.
I actually can't remember what jacket. I think this was a 90-degree jacket.
You're the one who created this page.
No, I put the table up right there before I put up.
I'm not blaming you. So these are rough numbers. I think according to the formula, 14 gauge and 12 gauge can actually take more, but they've been derated for standardized use to 15 and 20 amps.
Yeah, there's a difference between the current capacity of the cable and the maximum allowed circuit breaker or overcurrent protection you can put on that cable. So
Yeah. And
the last column on the right is actually kind of interesting too. Fusing current, a current that large or larger, it doesn't matter what conditions it's in, the wire just kind of explodes.
Oops.
The wire itself will blow like a fuse at that many amps.
awesome. I can see they stopped carrying at one point.
Well, that's more than you can carry on 2,000 MCM cable. So you probably aren't going to use anything bigger than 6 gauge as a fuse. Ever.
Okay. And so everyone get why it's important to, currents, they get hotter, they'll eventually explode. Does it make sense why you can only run so many amps through certain cables?
What do you connectorize 2,000 MCM?
I don't want to know.
Torch?
It's not a field connection.
We use this like a pyrotechnics chart?
When you get up into the MCM cables, the really heavy cables, some of the stuff like 250, 500, you can sometimes get Camlock connectors to work with. There are there's some weird varieties of Camlock. When you get up into the 1,000 to 2,000, this is feeder for an industrial site. This is what the power company would wait. This is not something
Okay. Those are your approximates. Okay, so voltage drop. It's a concept I mentioned a couple times. Is everybody happy with the table? Cool. Yes. Awesome. So voltage drop. Wires have resistance, and therefore the longer in resistors add up in series. So when you put them after each other, since a wire is essentially one very long, very low resistance resistor, the longer it is, the greater the resistance over the wire is. And due to our earlier equation, V equals IR, the greater your resistance is, the more it's going to cause your voltage to drop a bit. Or if you think of like a really long water hose, you lose water pressure at the end. Kind of the same. Tom's giving me weird looks. Analogies. So the important thing is, if you think you're pushing a certain voltage across a cable for your math and it's really long, it will actually be slightly different, and you want to take account of this fact if you're doing ME work. Smaller wire is a bigger problem because this is a bigger problem because you already have lower current limits. So when you're losing voltage, it has essentially a greater effect. Damn it, keep doing that. Will this work? No. The end button is right next to the arrow key, which apparently is really inconvenient.
So use the space bar.
I don't like the space bar as much. It only goes one way. Okay. So now what?
So what happened during a fall concert with the Soka?
Oh, yeah, that's a good story. I meant to tell that, and I forgot. Thank you. Okay, so during fall concert last year, there was a run of 16 gauge Soka. Let's see, 16 gauge is not on this chart, but apparently it's less than 15 amps. 10. It's 10? Okay. And it's Soka, it's a multi-connector, and one of the factors of your rated current capacity is whether there are multiple other hot current carrying conductors next to it, because each of them will produce heat, and if they're all in a tight bundle, the heat can't escape as well. Therefore, they will kind of heat up faster, and it is a greater risk to all of them. Therefore, you want to reduce the current on the max current capability for each of them to prevent fire. So this is before we started thinking of all of that. So during fall concert last year, there was a maybe 200-foot run, 300-foot run of 16 gauge Soka, which ran from lighting PD, or it broke in from one of the PDs. I'm guessing the courtesies on lighting PD. Wasn't a little coil because we had some extra cable, and then ran along the floor up and over to a truss where each of the 6 wires had a VL2500 on it, which draws about 12 amps at 120 volts. What?
But what happens when you, never mind, keep on going.
They draw like 8 amps and 120 volts, but the voltage drop, they draw
Right.
more current when they have a lower voltage.
Right, I'm getting there. So, really long cable run, really thin cable, and heavy load at the end, and all of them were in use. So really, this was the wrong setup, and part of I don't know if it was 16 gauge the entire run, but at least the bottom part of it was, and the bottom part, that was connected to lighting PD. However, since the run was too long, because Soka is kind of long, and you can't always get it in nice, and you can't always have your objects 100 feet apart, or 100 feet multiples, there was a coil of it sitting next to lighting PD. Because it was over its capacity and in a nice coil, which put more conductors next to each other, thus making it harder for the heat to escape, this cable caught on fire. And
Is it flames or just smoke?
flames. Mike, were you there for this incident?
I was, yeah.
Would you like to continue the story from here?
Well, the insulation on all the cables melted, which meant that all the conductors were now not insulated from each other, and they started touching and just sparks, and it was bad.
Since then, we have thrown out all of our 16 gauge Soka because it's not worth the trouble, though it is worth the money to sell it. And we now pay much more attention to these kind of principles. Yeah, that's the story. Surprisingly enough, a similar thing happened to Apollo 13, except that they kind of just baked their cables and then decided to run current through them and exploded them, or exploded the oxygen tank that they were in. Because that's what happens when you burn off the insulation from your cables in a tank of oxygen.
The way I heard this, that it would not have been a problem if it
it was still bad.
Okay.
We still probably shouldn't have been doing it either way.
So, Ben, what you can do is if you need to have a long cable run, you increase the gauge of your cable, because if you go back to the chart, if you increase by 1 gauge, your resistance per foot will go down, and then you'll have less voltage.
Not only, and additionally, your current capacity will go up. So it becomes less of an issue on 2 different ways. Either way, it's a win, except for weight. What?
So what should the NE done that code during the last DS decided to coil all the feeder in a little box?
Not.
Should have gotten the 25-foot jumpers. on
However,
too.
because he was using a larger cable and it was not even close to the capacity of the cable, it did not catch on fire.
I thought it was
Also, it was an enclosed box, so even if it did catch on fire, I don't know how long the fire would have lasted.
a long time because that box is open. That box has holes in it.
Oh, well,
Many holes.
there we go.
What was on that distro? I think it was
Lighting PD and then LPD.
yes,
70
but
amps.
that's not an answer.
What?
Yeah?
Does the disconnect have a circuit breaker on it?
It has a form of circuit breaker.
It's a fuse.
Oh, it's just a fuse. Okay.
Okay. We're getting to that in like 30 slides. So voltage drop. It's important to take account of. We've learned why. Okay, connectors. Now here comes the fun NEMA section. Loved making the NEMA section of this slideshow. So NEMA is a standards organization that standardized electrical connectors. You may ask, why did Ben bring all these cables? Or why does tech use so many different types of cables? Well, because not all of them are for the same things, and you don't want to easily be able to connect the wrong things into each other, or you will blow stuff up, as we have found out. So there are a series of locking and non-locking connectors. They prevent you from doing stupid things, and unless you were really trying.
Don't we spend a lot of our time making cheaters so that we can get around that?
We do, but there are rules that we follow. So different connectors are for different voltages, currents, and number of poles. A lot of our cheaters are designed so they can cheat things that are actually compatible with each other and just otherwise would not fit. However, some of our cheaters don't do that, and we will talk about why those exist, or should not exist, because I brought some with me. I know, it's fun times. So in this section, one of the important things is the naming convention, and I created this style guide for how the naming convention works. There's no real official way of labeling the symbols, so I just made this up. But the first symbol is locking. You will get an L there if the connector locks when you insert it, or you can lock it in place. If there's nothing there, it's a non-locking connector, followed by a number. This is a wire designation. It doesn't tell you how many poles explicitly, but it's an indicator for the class of cable, and it will tell you how many hots it's supposed to carry, whether it has a neutral, and whether it has a ground. Yes, there are cables that lack ground, and there are ones that lack neutrals. Then there's a dash, followed by the number of amps that the cable next to it is rated for, and the connector is rated for, and then a P or an R, which indicates whether it is a plug or a male or a receptacle or a female, although some cables are weird and act both ways, or you can't easily tell. Although often if you're talking about the thing as a whole, you can drop the P or the R if you're not talking about the specific piece of hardware. There's also others like outlet, which is kind of just a receptacle in a different form factor and stuff like that. So I have examples. There's 515P, which is it's number 5, which means it has 120 volt hot, a neutral and a ground. It's rated for 15 amps, and it is a plug, and it looks like this. There's L620R, so it's locking. The 6 means that it's got 2 hots and a ground, rated for 250 volts between them. The cable is rated for 20 amps, and it's a receptacle. And that looks like this. And L2130, so locking. 21 means 3 120 volt hots neutral, neutral and a ground, 30 amps. And that guy looks like, and I dropped the P or the R, so it's either one of these guys. It's ambiguous because you're talking about the connection as a whole, not an individual piece of hardware. So with any kind of weird naming convention, you have a beautiful chart of everything in it. This is not everything in it. This is just a significant subset that you may encounter in real life. Also, if there is an orange box, it means that you're likely to see it on tech. So you have your 515, your 520, L520. So these two are actually safe to connect to each other because they are the same plug. They just either lock or don't lock, and that's why cheaters can exist for them. Your L1420, 2130, and L620. Just a note on notation, green means it is a ground, white is a neutral, and black is a hot or pole or line.
Welder or plasma cutter?
Not for the 1430 is, yeah. Oh, wait.
Plasma cutter?
Yeah, apparently L620 is used for welders and plasma cutters. We use it for moving lights. What do you know? If you get a welder, you can probably power it off our gear.
Probably not on the sound side.
Yeah, the sound guys won't like it. So now is the fun process of going through all of these in slightly greater detail. So first, NEMA 115, 515, and 520, also known as the Edison plug. I don't know if Thomas Edison invented it, but it's named after him because he did something with electricity, I don't know what. It's non-blocking 120 volt, and it's pretty much the plug you see everywhere in the US, not in specialty installations. It's what you see in the walls. The 115 is a standard 2-pin connector, and it used to be in older houses. It looks like this. You have 2 pins, and they go into the wall. It's rated for 120 volts and 15 amps. Plug-in receptacle. By the way, these diagrams are all the receptacle side, so it's what you see if you're looking at the receptacle of it, not the plug. One hot, one neutral. Although conveniently, the plug will also fit into a 515 receptacle. You can see the pins are the same. And the 515 plug will fit into the 520 receptacle because the 520 receptacle usually only has this T shape because the 520 plug is actually the hot is vertical and the neutral is horizontal, which is a convenient factor about them. You can plug lower current devices into a higher current circuit. The problem with this is if most likely the wire behind the plug is not rated to the current capacity of the circuit breaker of the outlet, which could be a cause of fires. So your 515 is the standard one that I don't know when the regulation went into effect, but while ago. But now you really only see 515s unless you're in an old house, in which case all your 515 devices will want to plug into 115 or 115 receptacles unless you need this guy. And then your 520 is the 20 amp variant. You don't see the plugs that often, but you see the receptacles a lot because it's convenient to just put 20 amp breakers and the 20 amp version of the receptacle in buildings, and you get the 15 amp can plug in as well. So here's a pretty picture of all of them. You have a 115, a 515, a 520, 515, 115, and then here are your receptacles all nice and next to each other for comparison. And for someone who has not been to this presentation before, there's a 115 in the top left corner, 115P in the top left, and a 115 in the bottom right. Can anybody tell me the difference between them?
One of them's got the little knob at the end of one of the things.
Which one?
That one, right there.
Okay. What does the knob mean?
It means that you can only put it in one way.
Okay. Excellent. So if you look at the diagram, you'll notice that the receptacle on this side is slightly wider than the slot on this side. This is to polarize the connector and prevent you from plugging the hot into the neutral and the neutral into the hot. Some devices are wired in such a way that that could be bad. Lamps usually don't care, so you probably won't see a grounded polarized plug on a lamp, but you do? Okay.
Because you always switch the hot.
Okay, yeah, anything with a switch, you want to have the hot go in. And actually, one of the Build 18 projects, they wanted to put a switch in that could be controlled by an Arduino on a relay, and they were hooking up to a water heater, and they didn't know about this, so they put the neutral through the relay and the hot straight through, and it could have been bad, but they got stopped. But
Why is it bad?
because even if the relay turned the neutral off, there would still be 120 volts AC on the body of the water heater with no path to neutral, so if something went wrong or there was water spill, it could be dangerous. There was no ground. It had a 115 plug on it. Exactly.
So then what purpose does it serve in a thing with that ground?
What?
What purpose?
So the purpose of the neutral is to complete the circuit.
Yeah.
You get 120 coming out of here, it flows through your device and back into the neutral. The ground is if something goes wrong, it provides a path for the voltage and the current to get back to the safety of the circuits and not go through something else that may be convenient, such as you.
Okay.
Isn't there just some random wire connected to the edge of the device that goes into the ground?
Usually. Usually the case of a metal device will be all connected to ground, so if there are any wires that somehow get loose, instead of shorting to open space or to you, they short to the body, which will then go to ground, hopefully through a low resistance path, so it is the preferred path for the electricity to go through. Additionally, a lot of things will check the current on the ground, and if it goes above 0, we'll turn off the power. Some things will turn off the power on the hot, therefore stopping whatever could be wrong.
Actually, they check for balance between hot and neutral. They don't touch the ground itself at all.
Okay, I'm wrong again. Excellent. So there's the pretty pictures. So you can see these guys are both the same width and they're narrow. This guy has a slightly wider plug. Usually don't see the wider plug on the 515s because the ground pin kind of polarizes it and keeps you from plugging it in backwards.
What is the purpose of the T connector on that 150 rod?
I don't know. I'm guessing this part of it is actually a 120 connector, but I couldn't find any pictures of it to verify that. Mike?
I think that's a 10 amp if they're both sizes.
Okay.
Actually,
It's not
if you
too
reverse the hot instead of the neutral,
Mm-hmm.
you're at a 240 volt plug.
I've seen those at like my high school.
But
It just gets weird.
They're old.
yeah, but you see this plug everywhere. It's your family of 120 volt, 15 or 20 amp circuits and plugs and receptacles and all that. So now the L515 520, this is surprisingly enough exactly the same, except it locks when you plug it in. And I have an example of that. This quad box has your Edison 520 receptacles on it, but the plug is L520. And this is because SoundPD has 3 L520 receptacles on it, specifically for this guy. Or does it have 6 520? I thought it only had 3. 6? Okay, 6 520s. Okay. But this is, we use it for stage power. My high school actually had these plugs for all the lighting instruments, but it's 120 volt, 20 amp. Exactly the same, just different shape, and therefore this thing is completely legal and fine, with the exception of if you have a dimming system that uses 520 as that, you don't want to plug something that wants non-dim power into this, because this is usually for constant power. So that is the one case where it might be bad. L620 is the big brother of that. 620 the 6 means it's got 2 hots and a ground, so it's rated for 250 volts or 208 volts. They're really usually rated for 250, and therefore you can plug anything less into them. But we use it for 208 or 240 volt, and you get 20 amps with it. This is just to show you the difference between the 520 and 620. You can tell the pins here, the wide one's in a different place, and they're slightly farther apart. And I have a 620 receptacle if you want to look at it. And I think there's a 620 male somewhere as well, but
Look on the other end of that thing.
There should be an extension cable.
Oh, it's not.
here it is. Here's a 620 female, male receptacle plug. Here's just the receptacle. If you want to look at the L620 closer, it's up here. Just shout or cry or something. So this plug is usually used for tech and drama now for our moving lights and anything that wants 208 volt power. L1420, getting a little more exotic. It's got 2 poles, so it has 2 hots. Each of them is 120 volts relative to the neutral that it carries, and there is also a ground for safety. And so this one is used for more distributing power. In fact, I have a demo unit of this. I have this quad box, which has an L1420 male on it. It's used for front of house power because front of house usually wants 2 circuits. And the nice thing about this quad box is it gives you 2 separate circuits. So one hot goes to these 2, one hot goes to these 2. You don't get 208 volts between them just because this isn't wired that way, but it gives you 2 circuits over 1 cable, which gives you less cable to run.
Why wouldn't you get 208 volts between them?
Because none of these plugs are currently wired or rated for 208 volts. You could if you plugged into here and here.
That's what I mean, if you went between.
Oh yeah, if you want these 2, then you could. But you really should not be doing that because you don't have a safe plug for doing that. So we use this for front of house power, so front of house can have,
See a quad box up there that does that.
what?
Did that.
Which one?
There's a reason that it is that.
This one.
Oh yeah, that guy we're getting to.
Yeah.
Um,
Also, this one and this one.
you stole two things on over there.
So if it's well safe.
Stop stealing my cables. But 1420 gives you two hots, a neutral and a ground. Gives you two phases on this guy. We use it for front of house field power. We also use it for motor control. That way you can have your up and down in different directions, and they both go through the neutral. Whichever one completes the circuit, that's the way the motor goes. Alex?
So when you cheat all 1420 into two separate Edison circuit thingies, don't you have like half the? Oh wait, aren't the phases balanced or something? So like.
You want to balance them?
It's like this.
They're not balanced by any rule other than knowing what you're plugging into them and balancing the current draw.
If you don't do that right, then like you could possibly have an issue with like having like neutral.
You have to be careful not to overload the neutral.
Right.
And
Be-
also about the motor power,
Yeah. Is it one hot and two neutrals,
it
or?
might work that way because AC doesn't really know which direction it's going. There's a separate control circuit that actually does that.
But we use it for motor control. Here's the fun one. L2130. Isn't that a beautiful picture I found of it?
It's so high res.
I know. It was even bigger. It was like 4 times the size of the slide. I had to shrink it, unfortunately. But,
Let's have another slide with only that.
well, I tried, but I need to have some text on it. This is a locking. It's got 3 hots, neutral and a ground. Each of the hots is rated for 120 volts to the neutral. And this is convenient because those are the same 3. We have 3 hots coming in, and they're all 120 volt. So this is all of our power in one cable. So I brought a 5-foot jumper. You have your male and your female. This cable actually is useful because a fun fact about connectors, you'll notice they're usually bronze. However, if you're looking at one or putting them together, you may find one pin that is silver. That silver pin is indicating that that is the neutral connector, or it's supposed to be the neutral connector. So you can see the plug receptacle, 120 volts to neutral, 208 volts to another hot, and it's rated for 30 amps. This cable is actually 8 gauge, which itself is rated to approximately 50-ish amps, depending on conditions. So if anyone wants to look at the beautiful 2130, if that picture is not enough for you. Also, a quick note, when you're dealing with these 3 phases at 120 volt, they're usually color-coded. Black is X, red is Y, and blue is Z. Just a fun little thing, in white is neutral, green is ground. Okay, stage pin, which I also have an example of buried. So stage pin is rated for 250 volts, usually 15 or 20. It's rated for 15 amps at 250 volts or 20 amps at 120 volts. It's usually used for dim power on conventional instruments. I don't think it's rated for 20 amps at 250 volts. No, it's not. Okay. Unlike the other guys, this is not a NEMA connector. However, it's fairly standard in the theater industry and entertainment industry. All of Tech's and Scotch & Soda's conventionals use this as their power connector. If you look very carefully, that one's actually not a good example. The ground pin is slightly longer than the others. Yeah, this one's good. You can see very carefully the ground pin's slightly longer. It's also in the middle. The neutral is next to the ground and the hot's by itself. This one's also clear, so you can see the cable inside of it. So you can see the green is ground, the black is the hot, and the white's the neutral, following the convention we've seen everywhere else. I'm not blocking it. So you can actually, if you're really stupid, plug it in backwards, but it looks stupid when you did that, so don't plug it in backwards. I'm just saying the pins are spaced so that they fit, but you're stupid if you do it. Oh, look, it's a 515 plug in 515 receptacles. I brought a quad box. Yeah, so we usually use this for dimmable. Hot pin's all by itself, the ground is longest. Hopefully you've seen this connector before, if you've ever done. Red cover means it is for 250 volts. What?
Red cover might mean it's for 250 volts. It might also mean someone got a
So if there is some kind of standard, know what that standard is, and don't assume that if you go to a random place that any kind of convention is followed. If you see something, always ask. For example, this connector. Ask whether it's dim or non-dim, whether it's 120 or 250. If you just see a line hanging somewhere, don't assume things because
Dim means contact.
what?
What does dim mean?
Dim means it's dimmable, so the voltage over it can vary from 0 up to the max of 120 or 250. Non-dim means it's always going to be at that max voltage.
I think the simpler answer he's looking for is whether you plug it straight into the wall or whether it goes to a dimmer.
Okay.
So when you have a light and you can make it brighter or dimmer,
Yeah, no, I mean, I get that, but why would a wire not be able to?
well, the wire can be, but often you use I've been saying, like, you use them for different things. And if you make and if you know that there's some kind of convention that this is only used for dimmable power, you won't want to plug a computer into that because computers don't like being on dimmable power. So it's a way of using different connectors for different things and keeping problems from happening just by don't plug things into each other that shouldn't be together. And that's why we have different connectors in all these guys. Cool? Awesome. Camlock, our big power connector. This is used for when you need more than 50 amps. So basically when you're hooking up to the wall to power your entire rig. They're color-coded with the standard convention of white is neutral, green is ground. And then you have hot, hot, hot of red, black, blue. Depending on the connector and what you're connecting it to, the 90 and 180 thing isn't official. However, with text gear, pretty much everything except lighting PD will let you turn a full 180 degrees, and therefore you should do so when you're plugging it in, plugging in Camlock. I've been told 90 degrees locks it in place, 180 degrees waterproofs it.
They're waterproof when fully inserted without rotating.
They're also apparently they're also really mechanically strong. Tom, if you want to share that story again.
That we lifted the end of a generator with one by accident.
Yep. Was it only 1 or 5 of them?
It was probably one taking most of the strain.
Okay.
Also, Tech also owns a 15-inch pipe wrench for getting these things off when they stick to PDs, which they do.
Yeah.
Yeah.
So don't tighten them until you break them. Tighten them until they're secure, and they won't get yanked out accidentally. The direction convention varies. Usually, this is actually the female because it has the receptacle of the copper. This I'm considering the male because it has the plug of the copper. And you'll get these for the hots coming out of the disconnect or your wall. And some places will either have the same for all of them or just the neutral reversed or just the ground reversed or both reversed. The way we do it here is the neutral and ground are reversed, so you can't accidentally plug a neutral into a hot or vice versa. Although I believe one of the rental houses does it, only the ground is reversed. Mike, do you know which one?
Yeah, Trap, I think that's.
Okay. They only reverse ground? Okay.
Chuco reverses too. We actually picked the convention up from them.
Okay. So I brought a Camlock connector with me. In fact, it's a splitter. So this splitter or twofers, hopefully you can figure out, they let you plug 2 things into one.
We should not use that as a jumper for just one thing.
Yeah. If you're using it as a jumper, you're either desperate or doing it wrong. And if you are using it as a jumper, you should severely tape over the one that's not in use. But just don't do it. So this is green. What does it mean? Ground. Thank you. Hopefully that's not difficult. It's right here.
It's funny, the only person in the room who can't see green got that right.
You should all be proud of yourselves. If you want to play with connecting or disconnecting this, don't let Tom connect it before you try to disconnect it. If anybody wants to.
Oh God.
But when you're making them, you can see these are the internals. There's actually a complex process that people like Ty Tut know. And part of it this actually tapers down a lot, and you cut it at wherever your cable is, or whatever the thickness of your cable is, including the insulation. And we use this for big power and hooking up. And we'll talk about more of that later. Anybody want to play with it? I found a pretty picture of a bunch of them. It's kind of like when the Air Force takes a picture of their airplane surrounded by all the missiles that it can carry. This is just a bunch of Camlock connectors surrounded by all their parts and caps and pieces.
One yellow.
I found it on Google.
Mackie, is that a website?
So, neutral, ground, hot, hot, hot. The yellow and the orange are used for hots in different countries when you have 600 volt, I believe.
Yeah, orange is that wild leg on the weird three-phase.
Okay, orange is the wild leg. Also, the color convention varies depending on where you are and what the voltages are. Yellow is a hot in like 600 volt. Same thing with, orange.
There's some odd conventions. There's a couple other versions of three-phase that you didn't talk about.
Yeah.
Like a delta where you actually ground one of the corners, and there's two hots and a grounded connector, but you still get three-phase. Yeah, some of that stuff just gets weird.
We're sticking to the nice easy.
We don't do that.
Stick to the nice easy 12208. But you can see the wide variety of colors that you can get and the different pieces of them. They also come in multiple sizes. We have a baby tiny one, I think, or sometimes you see one cable that just has 5 baby Camlocks coming out of it. It's so cute.
Oh God, that thing.
It's cute.
No, it isn't.
The rides folks use them at Carnival.
Okay.
If you look around, you'll see them use some.
Yeah. So that's Camlock. Everybody happy with Camlock? Yes? You raise your hand. Yeah. Okay.
Replacement convention for how they're strung up? I don't know if
The
red, green, colorblind people have a problem.
red, blue, green should not have a problem with it. It's usually ground, neutral, hot, hot, hot. So red, black, red, blue. I believe it's black, red, blue.
It's generally black, red, blue.
Yeah, black, red, blue.
There's one other thing you can sometimes run into when you get 6 Camlock connectors.
Is double neutral.
When you get a double neutral.
Due to I mentioned earlier that inductive loads are difficult to do math with because they shift the current around or the current part in time relative to the voltage. And an effect of that is instead of the phases balancing each other out, as which usually happens with resistive loads, you can have multiple phases worth of current all going through the neutral at once. Therefore, they're not balancing out through the other hots. So sometimes on dimmer racks, you get 2 neutrals to carry the additional load.
Hey man, why was that cable that we had at the Guster concert that was Camlock into an L2130 plug bad?
Depends what the Camlock was rated for, but it was probably more than the 2130 or more than 30 amps. So that's Camlock. More connectors. IEC 60320, 13 and 14. 13 is the female and the 14 is the male. You'll often see this connector on the back of your computer power supply, or servers, lighting consoles, sound consoles. Anything that's usually like a desktop appliance or similar to one will usually have this connector as its power cord. It's rated for 120 or 250 volts, 10 to 15 amps. It's not intended to be carrying for a whole bunch of things. It's for one computer or whatever. I'm sure you've seen these cables. They're everywhere. Well, yeah.
Typically, deck stations and old MacBooks old Mac towers used to have the plug that you could daisy chain several of them off.
Yeah. Well, some older computers used to have one so you can daisy chain your monitor out of it. But that's what this is for. Server racks often have a rail going down the side of these guys, and then you have male to female cables of just the 1314, which then plug into all the servers. So I'm sure you've seen this before, but if you want to play with it, it's up here. Most of them. A lot of racks have that. That's how they deliver power to all the servers.
Never seen that.
Oh, really?
Yeah, it's pretty common.
I've almost always seen it.
You sell the same rack to anyone in any country. The point of the IEC connector is mostly to avoid the localism, a local flavor of electrical.
Thank you. So yeah, anything that's like a computer or goes with a computer and requires wall power is most likely going to have this connector on the back of it. PowerCon. It's a locking 3-pin, 120 volt, 20 amp connector. It's made by a company called Nutric. They also make a connector called Speakon, of which the name and design is derived from. However, they're not compatible with each other. The Speakon connector, I believe, is designed in such a way so all the pins are internal. Thank you, Tom. So when you are, because speakers, sometimes, or at least older ones, you had to put a very high current through them to drive them, and therefore they wanted if there was an amp hooked up to a cable and the cable was by itself, they wanted it to be a safe connector, so you couldn't hurt yourself with it. So they put all the cables internal, even when it's not connected. So there's a blue and a white variant. You'll notice this connector is kind of a weird mix of male and female. The blue one is for delivering power from the cable to the outlet. The white is for delivering power from the outlet to the cable. So on some devices, you'll see like the text TRXs, the LEDs, you can daisy chain them. So they have a blue as the input and a white as the output. So then you can plug it from the output of one into the blue of another and pass it on down the line. And yes, the blue and the white are different shaped. They have the nubs in slightly different places, so you can't plug them into each other, and therefore maintaining the directionality of power so you can't cause problems. Anybody want to play with these? No? Okay. They're
Do they make like things that you can connect? You can like daisy chain like two.
Yeah, they have barrels, but they're going to be blue on one side and white on the other. Once again, to prevent you from messing things up. Speak on has both ends being the same because there's no direction. Yes?
These are not just 120 volt. Okay, they may be 120 volt connectors.
They're also
but a lot of
250.
people use them.
Yeah, okay, yeah. I forgot to label that. So Tech uses them on the TRXs, Traps VLXs also use these, and the 108s use these. So yeah, blue and white, they're two different types. California is an old, weird, non-NEMA connector, even though it looks like them, that is capable of 250 volts. It's got it's actually a bunch of different variants. I think we use the one that has 3 hots and a ground, 2 hots, a neutral, and ground. Sorry, I got the picture of the 3 hot one. They're all very similar. Yeah, this is the one we have, X, Y, neutral, ground. You see, the pin in the middle is actually useless because it's for aligning the plug, but if you really need a giant pin to align your connector, I don't know what's wrong with you. So I have an example of this. The ground is the bit on the neutral, not the pin as most people believe. So I believe Brock has taken this out and Tom have taken all of our gear away from this connector onto either nothing or NEMA.
They're at L2130.
They're 2130 now?
Yeah.
Beautiful.
When you do the ME lecture, we're going to have an exciting discussion about how those are wired. But,
I thought you were getting
yeah.
Okay. But this is a 50 amp connector, so you can shove 50 amps down this. It's more than 2130, but it's not NEMA, and it used to be on our KF rig. So if you came for orientation, you would have seen this connector and been like, what the hell is this thing? Until someone, what? Because it's not really standardized with anything else. 2130, we're standardizing a lot of our gear to, which makes it easier to work with, and we all know what it is. California is an older, weirder connector that it's kind of used in Hollywood. I guess that's why it's California.
It also doesn't play, it's a temporary power connector. It doesn't play well in a 3-phase system, and we're almost entirely 3-phase now.
That too. So California, I'm showing it to you because it existed on Tex Gear and you may occasionally see it, but hope that you don't. Socapex, also known as multi-cable. It has 19 pins, or 6 sets of 3, and then 1 lonely pin in the middle, which if you're using lighting, you probably don't need. Its rating depends on what type of cable it is. So you can have 12 gauge, 14 gauge, 16 gauge, whatever. There's different variants with different numbers of pins. You can find them with more or less. Usually use it for dimmable power, so you only have to run 1 cable across the stage instead of 6. It's also used for speakers. If you were at the Guster concert, you would see that they had a variant of Socapex that had fewer pins, and they were running their speaker towers off of that, which was kind of cool. But if you're using this for lighting, I divided up the connector to show you that these 3 pins are 1 circuit. You got hot, neutral, the grounds are all in the middle. A 2nd circuit, and you get 6 of them kind of like a pizza around the connector. And I brought a Socapex male with me, and you can see that it is also divided up the same way, and it has labels for line, neutral, and ground. So if you want to take a closer look at this, some problem you may see with these, or one annoying thing about these is the connections are all soldered on the inside. which means it's not really field serviceable, unlike a lot of the NEMA ones, which you only need a screwdriver to fix. This you need a soldering iron. Also, sometimes they become like rotated by 16.5 degrees, and therefore your circuits don't really line up anymore, and you may get weird off by 1 errors. That's there to play with if you want. Also, yeah. Also, you see it has 6 stage pin. Yeah, thank you. That's the word. 6 stage pin connectors on it. Yeah. LC is lighting cable. That is a connector. So it's not only for power. We use it pretty much only for power. Okay, now we're done with connectors. Is everybody happy with all that? / have any questions before we move on? Was there enough NEMA for you? Okay, circuit breakers. These are devices that you put in your circuits, and if more current is being drawn than they are rated for, they will automatically switch off. You can also switch them off yourself if you feel like it. If you don't want, if you want to turn off a circuit, here is a nice diagram of the inside of them, and they prevent damage to hardware, cables, and people. Because if something's suddenly trying to draw 100 amps instead of the 20 it's supposed to be drawing, there's probably a short somewhere and something's wrong. So this is a safety device that turns it off. They're also made to somewhat high standards because you want to be able to load up a circuit up to its rated value, but you want the circuit breaker to trip when it hits that rated value and not 10 amps over. So they are somewhat well designed to be at a very particular value. So I have a couple boxes that have circuit breakers on them, and you can switch them on and off if you want. I will explain these boxes more later, but if you really insist on playing with the circuit breakers, they're there. The circuit breakers make sense? So if you notice, this box just has 3 breakers on it. You also get multiple breakers, and if you notice, a lot of the cables have multiple hots. If either one of the hots is suddenly drawing more than it's supposed to, or you want both of them to turn off because something's wrong with the device at the other end of that, so you have multiple breakers. So there's usually, you either get 2 single breakers which have some kind of plastic thing over, and yes, when they turn off, they are forceful enough to turn each other off, or you'll get this, which just has breakers which are connected internally between the 2 of them, and even though it's just one little switch, it's actually connecting 2 hots and turning them on and off. And those are also available to play with. So yes, this is one of our 2130 breakouts. On the big distribution boxes, you'll get triples for the 2130 outlets because the 2130s have 3 hots. Often in a house or building, you will get circuit breakers in a convenient panel. And this just provides a safe, convenient location for them all to be in. Inside, if you took the cover off, you'll actually see rails going down the middle that the circuit breakers are snapped onto, and those are for each of the hots and the neutral. So they can complete the circuit, and then the wires from them go out to the side and wherever. We have an old PD called Matatata. It's got 3 T's for the 3 mats that built it, which is essentially a piece of plywood with a big circuit breaker mounted onto it with a bunch of little boxes wired out of it. Yeah, and some feeder. Tom, Matatata?
I'd like to see it go away.
That's what I thought. You usually only see these in houses, but that's what they are in relation to circuit breakers.
Sometimes you'll see them on a piece of plywood strapped to a hand truck.
With FMS, yeah. I think FMS has something like Matatata. We saw it in Wigan for, yeah.
And Shuko definitely has one.
Yeah.
FMS is like a giant version of Matatata.
They're a poor man's power distribution breakout box. So similar to circuit breakers are devices called GFIs, or ground fault interrupts. You often see these in kitchens or bathrooms around a house. Or places where there might be water, and they're the ones that have the little test reset button, right? Or those GFCIs, and they're different.
CI is the actual name.
Okay.
There's other ones that have a reset button though. So.
Okay, they may be the thing.
Usually the red and the yellow reset buttons tend to be used.
Okay.
In black case.
So these are similar to circuit breakers in that when they detect something wrong, they turn off. However, instead of detecting overcurrent, they detect a difference between the, what? Oh, they do both? Okay, so they will detect when you draw more current than it's rated for, but in addition, they detect the current difference between the hot and the neutral, and if they're not exactly the same, meaning that there is a complete circuit on the other side of it, and all the current that goes out from the hot comes back through the neutral, and vice versa when the voltage is in the other direction, it will trip and turn off, meaning that if they're not exactly the same, there must be current going out, leaking out somewhere, which is either the ground or you or the fork you stuck in the wall or something. So these are often seen in places where there's water because they trip a little differently and safer. Also, you can't plug them into each other because of the way they work. They'll cause each other to trip. Anything else to add, Tom? Okay. You don't really see them on tech. They're just similar to circuit breakers, so Tom and I decided to mention them. Okay, so distribution boxes. So we talked about the big power cables, the Camlock. We talked about the little power cables, the 15 and 20 amp connectors. And you need some way of going from the big to the little in a safe way. So we have these distribution boxes, which will take in Camlock up to, I think, probably 400 amps. They might be rated for more. These guys will take 400 amps in, and they have a bunch of circuit breakers, including one big one on the front, which will turn off, which is connected to these three. They have convenient meters on them, and then they have a ton of outlets on the back. This is one of the new MLPDs, which have been named Zeus and Jupiter. Yes, they are both the same. And you get 6 Edison circuits, each with 2 outlets, 20 amps each. Each circuit has its own 20 amp breaker, and 6 L2130 circuits, which each has a 3-pole 30 amp breaker, and each of the 3 are all connected to each other. So any of the hots for this one trip, it'll trip the other 3, or it'll trip the other 2. And we're using these as our main distribution for both sound power and intelligent lighting. They also have meters, which apparently on all of them are slightly off, and they're recording less than the actual voltage, especially for 208 volt. So we might want to actually get those replaced. But they can also give you a rough estimate of the current flowing in through each phase. It doesn't measure the sum of coming in and then going out again. It's just going in through the main breaker into the rest of the box. They also the current meters don't really show for under, I think, about like 7 amps or so. So if it's showing 0, but there's stuff on it, there actually is current flowing. You're just not seeing it. And you can hit the bottom button and switch between 120 volt to neutral, hot to neutral, hot to hot, current, and frequency. Yeah?
The meters on the digital dimmer also read low.
Okay.
They read like 118, 117.
That's normal. It's more of these guys, when you put them into 208 volt hot to hot mode, they read more like 199 or 202, which is significantly lower than the approximately 206 or 207 that a Fluke will read. They actually have little probe ports here, and here along the top row here for sticking a multimeter probe into. So you don't have to stick your multimeter probe into here when it's connected, which is a bad idea. There's a reason these are covered.
Something else to be aware of on that, the main breaker doesn't shut off the other row of Camlock connectors.
Yeah, these are hardwired through, so this is a safety breaker for this stuff. So we've seen it, or at least a pretty picture of it. This is a prettier picture of how it is wired internally. This was fun to make. So you have your input Camlock connectors, ground, neutral, hot, 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 and your neutral and ground get run through and connect to the neutral and ground connections of all the output cables. Your hots each run through the triple circuit breakers, 1 breaker per hot, but they're all connected together, so if any of them trip, they all trip, which then run to the hot connectors. For the Edison outlets, you'll really only have a single circuit breaker, and one of the 3 hots will be there. For the 2130s, you get all 3 of them. Took a while to make, but I hope you enjoyed that diagram. And there are 30 amp breakers. Lighting PD is slightly different, and I'm going to include anacondas in this. Lighting PD is a semi-portable dimmer rack. It's portable in the sense that it's not built into a box attached to the wall and the floor. You can kind of roll it around on its wheels, although it's not fun. It accepts 5 Camlock connectors, same as these guys, although a couple of them don't turn all the way. I think the black is bad, and one of the other hot.
135, 90.
What?
The hots are 90, 135, 90.
Okay, so all three of the hots are weird and don't turn all the way. You have a digital to analog converter for doing your data for DMX. You have 4 analog dimmers, which are 2.4 kilowatts per circuit, which is this guy. You get 6 of them. However, you get 2 outputs, and you can do some fancy repatching on the back to change how those outputs, which are SOCA connectors, are actually done. You also have 2 digital dimmers, which have 12 channels each, but 1.2 kilowatts per channel. If you notice, that makes the total of each of them the same. 6 at 2.4 or 12 at 1.2. Gives you 48 total channels. Similar to, and on the analogs at least, I haven't measured the digital. The 1 and 2 are on the X phase, 3 and 4 on the Y phase, and 5 and 6 are on the Z phase. I tested that with Mike one day in a multimeter. I also brought an Anaconda, which is a portable version of that. What? I know. So this has 4 dimmers inside and just 4 stage pin connectors. It doesn't have SOCA because this is designed to go out and sit next to the lights that it is powering. You'll notice it has 2 515 plugs on it, also known as Edison. So you can get a total of 30 amps. It also has 4 fuses on the bottom, 15 amps each. It's one of them per dimmer. And this one, Alex took apart and probed around and discovered that 2 of them, numbers 1 and 2 are in this guy, number 1, and 2 of them are in this guy, and I forget which one, and the computer that drives it is on one of the 2 phases. I can't remember if these want to be in the same phase or not. Mike, you remember?
They don't want to go into the same outlet.
You don't want to put these on the same circuit because that cuts down what your circuit can handle, but yeah. Yeah. I think they're fine on 2 different phases, but okay.
Judging by your Odyssey, it doesn't make it.
Anacondas are also not supposed to make everything in the room buzz.
Yeah, but they do that. So Anaconda, it's portable dimming or more portable dimming variant of the big dimmer rack. What?
White noise, Anaconda is white noise producer.
Exactly. But they're portable dimming. You run them 2 circuits, and then you have dimmable power where you want it. And I believe they're 2.4 kilowatts per circuit for each of the dimmers. But that might be too much. What?
With those 15 amp breakers,
They're 1.2?
you're going to get halfway between 1.8.
Okay.
But if you try to run 1.8 on all 4, you're going to trip whatever feed. Because it's only 20 amp.
So keep in mind what this is drawing. Additionally, because it's a dimmer, it's an inductive load. Even though there's a resistive load sitting at the end of it, this itself is an inductive load, and thus you probably want to pretend it has a little bit more current draw than it actually does to account for that. So those are dimmers. If you want to play with it, it's there. It's heavy though. We also have L2130 breakout boxes. They either provide 3 520 circuits or 3 L620 circuits, which I actually found the box that's conveniently color-coded. And these guys, they take L2130 in with a male connector, plug a female cable into them, provide you with one breaker per circuit of whatever the necessary amperage is, and they also conveniently pass through. So if you're not maxing out the L2130 line with one box, you can run it to another part of your truss or your rig and power another box. Just make sure that with all the boxes coming together, they have to be under 30 amps per phase. So you can see black, red, blue, 1, 2, 3, same color convention. On this guy, we probed around and found where continuity was, and you can see where the black, red, blue actually line up on the connectors. With L6, because you only have 2 poles, there's not really a standard for which one's which, and I think there shouldn't be a standard for the boxes, but I think they are all standardized to the same thing. We should really double check that because it makes the ME math a lot easier because you can assume where you're putting your loads on your different phases. So if you want to look at these more, they're here.
Or just working groups of 3 and it doesn't matter.
Yeah. So this one, 520R, 320 amp circuits. They have these nice truss mounting. We also have one unit that doesn't have the nice mega clamp on it, and you can put it on the floor. It's got 4 receptacles, but still only 3 circuits.
6 receptacles.
I thought it has 4 receptacles per circuit, but only 3 circuits.
Yeah.
So you can still only put the same total on each one, but it's better for breaking out into, say, a bunch of instruments or something, which is why it's good for going on the floor. Whereas that one's better for going on a truss if you're going to put 3 single heavier loads on it. Then the 620, 320 amp circuits, but they're L6, they're 208 volt each, and everyone passes through for providing someone else with power. Cool? They're kind of like mini breakout boxes. And because they're like mini breakout boxes, I did a mini diagram. Hey, look, it's the L2130 connector again. The Edison one got 3 breakers. Each one feeds through to an outlet with one of the hots. Neutral and ground run through all of them directly through. It also passes through to the other connector. Simple. The L620, I pretty much made the exact same diagram, but with 2 hots going to each of the breakers, because that's pretty much what it is. And going down to the L6. These aren't accurate to that. I just picked them arbitrarily, although I might have actually managed to line them. No, I didn't. But you get the idea of how these are wired internally. So now, if you're using them and you're MEing a show, you can be like, oh, I know how this works, hopefully, to a degree. And hopefully all 4 of them that we have are all wired the same way.
There's wiring diagrams for those boxes on the wiki if you forget.
Okay.
But we do not have a wiring diagram for Sound PD.
Although Sound PD is essentially these guys. It just has a different layout of outlets.
I'm curious what the L1420.
Well, the 1420 is going to follow the same pattern as this. It's L6. 1420 just has a neutral as well. So the neutral is going to be passed straight through.
Yeah,
The
but
hots,
which one?
the hots are going to be some distributed between them. Try and balance your loads if you're ME. I mean, you can test it and find out, but it's L14 and L6 are kind of the same, but L14 has the neutral. So, disconnects. Getting near the end here. Disconnects are essentially really big switches, and for turning on and off really big voltages and supplies of current. They usually have the nice big switches that you can do, and it makes the circuit safe when you turn them off for hooking up or disconnecting your gear. They're all in a metal box to contain explosions, and you want to be aware of arc flash. So, quick question. When you turn one on and off, what do you normally do? You walk up to it, say, lighting power going on, and then throw the switch, right? You're lucky if you're alive. I have YouTube videos. Here's video number 1, and hey, look, there's my mouse. This is what happens when these circuit breakers malfunction. Or not circuit breakers, but disconnects. So if you turn it on and there's a spark, or you turn it off while there's a load going through it, it is possible and maybe even likely that a small explosion of this like this will happen. And the reason that they are made as a solid box, except for the front, and all the wires are inside, is so if this explosion does happen, all of that energy is directed straight out away from the wall. I have a second video for your viewing pleasure. So you can see the panel, the front door just blew out, hit him, and left his glove behind. And as you can see, there is a significant fireball from this electrical fire. This video, I think, is on one of a higher voltage and amperage than what we deal with, but the same concept applies. You don't want to deal with these in the wrong way, and you really don't want to be standing in front of them when you turn them on and off, because otherwise you will have a face full of exploding gases and metal.
What exactly burns/catches on?
The air.
While you're at it, hit the one in the top left.
Oh, this is a fun video.
This is a slightly larger example.
500,000 volt, but
Watch the truck at the end for scale. See the truck?
so that's what happens when you have current going through a connection and the connection is broken. Like water, the current will want to keep going. And if it determines that the air is a good enough conductor, it will go through the air. Or it might explode.
In theory, the disconnects have arc
Wait, there's a correct way to do this? Really? Oh, hey, look, there is. So when you're turning these on or off, when you're turning it on, make sure that it's plugged into something. You don't want to turn it on when the tails are just sitting, when the camlock's sitting out open, because that is a hazard. This has happened. It was not handled properly. If you see tails sitting out and the disconnect powering them is on, find someone and turn it off. What? Yeah. That's a different story. There is no story.
Story time.
During, I think, DS last year, it was discovered that a neutral feeder line had popped out of the Camlock connector and was just sitting there. And what happened is we tried to figure out, we ran over to tell front of house that he was losing sound and then turned the disconnect off instead of just turning the disconnect off right away.
Well, what you probably should have done is thrown all the breakers on the distro box to remove the load from the disconnect before turning it off.
Although it was being fed through to lighting PD, which I guess you also turn those off as well.
Those shouldn't be on.
Or Pagoda.
Negligible power unless someone actually has a light on.
What? Right. Point was, it was not handled the best way. However, the disconnect was thrown eventually.
So you just, if you see that, you just turn things off.
Yeah. If you see loose camlock that's floating in space, turn it off.
Plug it in.
What?
Just plug it in.
Yeah. Because then you have a lot of current that wants to flow and a very weak connection. And when you get close enough, instead of waiting for the connection to happen, it'll just go across the air and explode.
Weld the connectors together.
Or that.
Oh, whoops.
So for turning these on and off, if I have a disconnect here and the switch is over here, because they're usually on the right side, you want to stand against the wall to the right of where it is, clear other people out of the area so they don't get caught in the fireball, turn away from it, inhale, and then throw the switch. This is, of course, after you yell lighting power or sound power going on or off.
And why do you breathe then?
Why do you breathe in? Because if there is, in fact, a fireball, and you're like, oh, God, a fire, you don't inhale a bunch of hot air that's exploding. Face the wall. I think Tom said face away from the wall. A lot of people, I think,
Away from the switch.
do this or this. Don't do pretty. So a lot of this. So now, you guys, when you see someone who doesn't know this going and doing this, you can say, "Nice knowing you," before they maybe kill themselves. After you step back and inhale, just in case, if you don't like the person. If you do like the person, you might want to stop them before they throw the switch.
Also, you should stop them anyway, so otherwise we have like lawsuits and stuff.
Yeah, lawsuits are annoying. You might want to avoid those.
And they'll damage the disconnect, and FMS will take like 3 months to replace it.
Plus, it'll hurt the show.
No,
These are all very important reasons, possibly more important than hurting the person.
If the disconnect's going to blow, it's going to blow. It doesn't matter where you're standing.
You want to protect people, and therefore follow safe procedure when turning these on and off. Shut up about your filter warning. Yeah, the projector, oh, it went away. The projector needs a new filter. So disconnects, feeder, I keep mentioning them. Yes, there is, unlike most connectors, where you make sure there's nothing on, and then you plug them in, and if they're twist locked, you twist them to lock them. Feeder, you have a special procedure. When you're connecting, you connect the ground, followed by the neutral, followed by the hots in sequence, and make sure they're securely connected. When you're disconnecting, you disconnect the hots, followed by neutral, followed by the ground. And if you pay close attention to plugs, you'll notice that often the ground pin is slightly longer, because this actually enforces this convention on every single connector. It forces the ground connection to be made first, followed by the neutral and hots. This is in case there is a circuit happening that there's current flowing through it. The hots get disconnected first, and therefore the plug is still in the receptacle and ground is still established to prevent danger. Also, while plugging it in, the grounds can connect and kind of like level everything before the hot gets connected and the voltage is applied. So I actually forgot part of the presentation that I'm going to go back to, in that I brought a bunch of cheaters here, and I'm going to see if you guys remember anything, and we're going to talk about why some of these are safe and some of them should not exist. I'm going to go back to the NEMA table to help you out, even though not everything's NEMA. Any questions about like disconnects or breakouts? Okay. This connector's on top. You have a 515 female and a stage pin male. Is this a good thing or a bad thing?
The way tech uses it, it's okay.
It's a good thing.
As long as we're doing the
I would like to point out the argument that if tech uses it, it's okay.
Yeah. What is tech normally? What is? What is?
Tech uses it for
Not necessarily. What is this? What is this connector usually used for? Dimming. What is this connector usually used for? Depends, but usually almost entirely non-dim.
Unless you're using like an incandescent light bulb, then you could,
That was a special case at
like a lamp.
Lunar Gala. This is usually used for dimming. This is usually used for non-dimming. If you want something that doesn't want dimmable power, you probably don't want to plug it into something that is dimmable. This may not be a great idea. Also, this can be hooked up to 250 volt or 208 volt, and they may not have a red cover to indicate that. So you don't want to just go willy-nilly plugging this guy in, because you might fry something that only wants 120 and you're going to give it 250. So this connector is a maybe, but probably bad. How about this connector? You have same thing, 515 female and L515 male. Is that 515? No, this is 520. Never mind. This guy good or bad? It's iffy. It's good in the most sense, usually, because that's what you normally get. You're plugging into a 20 amp receptacle. However, if you have wires in here that are only rated for 15 amps, the breaker at this end is going to be a 20 amp breaker, and you could fry your wires before the breaker will shut them off. So this is another meh connector.
The problem comes in if you're using an extension cord. It'll let you plug a 15 amp only extension cord in, or even smaller than that, for the next 100 and some feet.
So that guy's not a great idea. I also have the reverse of it. 520 female, 515 male. This guy, good or bad? Yeah, it's good. You're going to be drawing, your breaker is going to go at 15, so unless you're plugging in something that really needs 20 amps, you'll trip the breaker, but you won't hurt anything. So this cheater is actually good and safe and happy. What else do we have? That's just a connector. If you want to see what the inside looks like, they're just screws. Usually also the ground is green. The ground screw is green. It's a slightly different coating to make it better, and also ground is kind of standardized for green. Also in some connectors, this is L6, you won't see it, the neutral pin will be silver instead of bronze. Why is this bad?
Well, that used to be connected to something.
Well, we've done that before. I mean, like actually plugged it in while holding the other end. That was stupid.
Yeah, because this cable lets you, exactly. This cable lets you plug in and then kill yourself at the same time. This has been described to me as a suicide cable, because it makes that very easy.
Can I point out that was not that came from the California device?
Yeah, that's what I want them.
Yeah,
It is actually labeled
if you,
Y, it seems. If you keep
yeah, if you ever encounter one of these cables, it's best really to either destroy it or tape up both of the ends so you can't use it and kill yourself.
Occasionally, our stage pin cables will look like that because stage pins, if they're not put on properly, have a nasty habit of falling off when they're under force.
So,
We had that happen during homecoming with drama. It was kind of embarrassing. Sorry. Like 2 stage pin ends came off during one end. 2 of techs.
oh. So this cable is a good cheater from circuit to death. So try to avoid it.
What's the NEMA number for death?
00000.
L0.
Yeah, it locks you in. This guy I talked about, yay or nay?
Yay.
Yay, correct. Just gives you, double load the neutral. So be careful with your load. Hopefully you're not approaching that.
We can do the L622 Edison.
Oh, hey, look, another death cable. Why do I have two of them?
Because
I don't want to kill myself that badly.
Because they came together with the California thing that they used to plug into that was even
Okay.
smaller.
This connector, 520 plug, stage pin receptacle. Yay or nay? Yeah. Everything that this could be hooked up to this will be just fine here. It might not be happy, but you won't break anything. And it's always more important to not break things than to, do stupid stuff. This guy, you got your power con and your 515.
Yay.
Yeah. The reverse might be weird because this might have 250 volt on it, but this as it is fine. You won't hurt anything. This guy, 515 female, 115 male.
Useful, but bad.
Not entirely bad.
You can tie
So
screws
if you look really closely, you'll notice there's a little copper thing coming out the bottom. That's actually hooked up to the ground. And if you're using these correctly, you plug it in and screw the ground screw on the wall plate through this hole so you have a proper ground connection. This is for old houses. However, most people don't. They just plug it in, and therefore there's no
Yeah,
more
you snap
ground.
off that ground thing. It gets in the way otherwise.
Exactly. So these are useful if used correctly, but probably shouldn't. But usually bad because most people don't use them correctly. So it's something to keep in mind. 515 male, 520 female. Yeah, it's fine. You don't normally see these that often because usually if you have a 520 receptacle, it'll have the T-shape and you can plug a 515 plug into it. However, this one's weird and lets you is only a 520 receptacle with a 515 plug for weird cheating.
What do we own that has a 520 plug? Because
I think we have one quad box, I believe, that has a 520 plug on it.
we have an
Some amps? Okay.
Some amps do, and black. And
Black is 515, red's 515.
either black or blue. Must be blue then. Has
Blue.
520.
Okay.
We'll find out tomorrow.
Okay, this guy is one of the ones you may see a lot. It has a 515 male and an L620 female. 515 male, L620 female. Yay or nay?
It is not
You're
normally
standing in front
capable.
of L620, so they can't see why it's weird.
Oh, okay. L620, 515.
So you can definitely undervolt someone.
Yeah.
We have a specific.
So, yes.
Our
Wait,
settings-
yeah, we're going from 1 hot to 2 hot.
Ah, you may notice something.
As it turns out,
So,
Well, so I'd like to point out that that's a very special cable.
exactly.
Because they're for the MLs, which will accept both 208 or 120. And if you're sending it at, if you're sending 120, then one of those hots that's on the 620 plug is actually neutral.
however, if you try to plug a VL3500 into those, the thing
Yes.
will not last.
So, yes, this is a very special cheater. We made it for our moving lights, which have switch mode power supplies that could accept anything from 90 volts to I think about 260 volts. So we put L620 connectors on them so we can easily plug them into the L6 breakouts and run them on 208 volt. However, in the case we need to run them on 120 volt, we made these cheaters. They don't care which plug is on them as long as they get somewhere in that voltage range and sufficient current. So with this plug, you can give them 120 volt. They'll use more current, but it's well within their safe operating capacity and standards, and they'll be fine. However, some instruments that have an L6 connector, such as a VL3500, only want 208 to 250 volt and will not be happy with 120 volt and will refuse to turn on. You probably won't break them. They'll just not turn on. At one point, there was a show where we had lights that had L6 connectors on them and they were molded connectors and we didn't want to replace the connectors or take them off. So we made Evil Demon Christmas cheaters. They were called Christmas cheaters because they had green and red tape on them that were the reverse of this. And they were bad. So they had a female of this and a male of this for instruments that could take 120 to 208 but had the wrong connector on them, and we only had 120 circuits available or 208 circuits available.
And that is horrifying.
It was a scary connector, and we swore that when we made them, they would be immediately destroyed as soon as the show was struck. This was DS last year. Mike, you remember that? Yeah. So this cable is fine. You won't hurt anyone. You might hurt some gear that isn't smart enough to switch or not turn on at 120. But you shouldn't hurt anyone with it. However, the reverse of this is very, very bad.
What happened to that? Is it dead?
Oh, we took them. We immediately took them apart as soon as the show ended. What? Did we really? No, I thought they were taking.
Part of it went away because it was like CS's or something. Like Jay had like.
Oh yeah, Jay Hut's borrowed connectors from the CS department.
It's also worth noting that if I remember correctly, Drama maintains a permanent stock of those connectors because their MLs are connectorized in ways which require that to be done on a regular basis.
Yeah. However, we do not, and therefore the reverse of this cable is very bad.
Drama also has some other controls on who's allowed to plug things in and the supervision.
Okay. Our last cheater, I believe. Yeah, it's our last cheater. Is this guy. It is a 515 male and a 2130 female. Is this guy good, bad, or just confused?
Incredibly useful.
It is not the worst thing in the world.
No, I dropped it. I'm sorry, cable.
Why is that?
It's used for running amp tanks.
Where's my 208?
When there's no real power distribution.
Exactly. So this is actually a special cheater that was made for our amp tanks, alpha and beta. This is from beta. Alpha has a longer version of this. That's why on the top it says I have long power. And what this is for is if you need to run those amp tanks somewhere where you don't have a 3-phase disconnect available to you, you just need to run them off the wall in a classroom or something, or Peter Wright McKenna for some small event. You use this cheater, which connects all 3 of the hots to the hot on this plug. Yes, and
It gives slightly less power than you think.
so it doesn't give, and because all the amps are all 120 volt based, they just run off the different phases, so they each get enough power. So if you're only running 1 amp or 2 of the amps and at a low, not near its capacity, this cable could actually let you use the amp tanks in places where they're not supposed to be used. This prevents you from having to rewire the amp tank every time you move it around. If you really need, this does not give you 208 volt power because all the hots are the same thing, so you get 0 in fact between them. But however, you do get 3 120s, which are really only, instead of 30 amps each, they're each 1/3 of a 15 amp.
No, they're all 15 amps each. If the others are 0.
Well, yes. They share one 15 amp connection. So this guy is confused, I would call it.
There's also it's also no longer in one piece, but there's the lovely California Edison cheater we used to have.
Yeah.
It's Edison to California.
Yeah, there used to be an Edison to California, which is
was fun.
what those demon cables were from. It lets you plug 2 Edison plugs in here and a California out. They're bad, as Mike is silently telling me. Never use that.
What's wrong with tying the neutrals together on 2 different
If you have to
outlets?
if you have to
But
connect,
you might not tie the neutrals together. Some outlets are flipped polarity.
so if you ever have an instance where you're connecting one cable to another, it's probably wrong. There are certain instances, as we've seen, where it can work, but try to avoid doing it. If you need to go from one to another, there better be a very good reason and very well-established standard of control of how that adapter will be used.
But how else are you going to get some length of cable when you don't have the actual cables you need?
Magic. Or you get the right cables. So that's pretty much everything I brought. Does anybody have any questions about everything? Anything I didn't cover sufficiently you want to know more about?
So does that mean everyone here is now an expert?
No.
Good answer. Just think on my shoe. No, it's not. Yeah. Okay, if that's it, I leave you with my beautiful diagram. Or finally, the last slide that you've seen a few times, and I know you wanted to get back to. So thank you for coming. I hope you've enjoyed this. The next session in this category is going to be how to be a master electrician, where the rules of covering like how to calculate the loads, balance your phases, figure out how to run a cable run or make a cable plot and do all that work will be covered in exquisite detail, so you can be a knowledgeable AME for a show and eventually become an ME and run the show yourself. In Soundland, there's going to be how to cable tech sound gear, which is going to be kind of like this, except with sound equipment and not power. And in Lighting Land, it's either going to be how to hang and focus a conventional instrument, which for many people is more difficult than it should be. And yes, or possibly how to set up and use a moving light console. It really depends on which one I manage to schedule first. Or if there's any particular requests for a training session that you really want, let me know and I'll try and organize it.
How to hang and focus a conventional light?
Yeah, it's going to be really. Yeah, if you have any comments or questions or criticisms about this, let me know so I can make future training sessions better. I hope you enjoyed it and hopefully learned something and didn't sleep the whole time. Hopefully, especially not through the explosions, because, you know, they're explosions. So yes, thank you. That was under 2 hours.
There's no corresponding plug.
Thank you, Mike, for filming.
Well, cables aren't heavy, there's nothing to plug them in.
I love you, TV.
But they're like is it verified that all
Love you,
the,
TV.
like, the boxes on there are gone?
Okay, thanks, everyone. Oh, also, everyone, these slides are on the wiki under the, I think, electrical knowledge page. So if you do want to look at them again, they are accessible for you. They're under, I think, electric power. So if you want to use them as a reference, which may not be the best idea, but you can do so. Enjoy.